So this brings us to the place where we have to acknowledge that electricity and magnetism are not different things, that they are two pieces that must fundamentally go together, in that you can't have current without creating a magnetic field, and you can't have a magnetic field without inducing current. So those two things together have led to electricity and magnetism being combined as a single word, electromagnetism. And it's from this idea that anytime you drive current, you end up generating a magnetic field. So I'm going to draw a wire for you, like so. And I'm going to let some current flow through that. Let's go with 5 amps worth of current. Okay, so if I have 5 amps of current going through this wire, then what I end up generating is a magnetic field that is traveling perpendicular to this current in all directions. So if you think about an object going this way, the surface that is perpendicular to this is a plane, right? Like a flat sheet going out in this direction. And the intensity of that magnetic field is going to drop as I travel away from this particular conductor. So if you think about that, the way the magnetic field is going to set itself up is as a series of loops. Around this particular conductor that are all in the same plane. This is very challenging to draw. Okay, so if you can see a series of circles that are centered on this particular current carrying wire. Now, as I go out from the center there, this circle is going to have a circumference, and this circle is going to have a circumference, and this circle is going to have a circumference. And basically what I'm doing is dividing the tendency to create this magnetic field over the circumference of these particular circles. So it ends up generating a tidy little mathematical relationship called the Biot-Savart law. Which says the magnetic field strength, which is a vector, is a constant, which is the magnetic permeability of free space, multiplied by the current being carried by this wire if you take that current and you divide it over the circumference of a circle that you're trying to measure at. Okay, so we are going to need a few numbers here. We're going to need mu naught, that's the magnetic permeability of free space, is 4 times pi times 10 to the negative 7, which is a nice tidy constant. Okay, so if I were to ask how, what's the magnetic field strength 10 centimeters away from this current carrying wire? So if I were to do that, I would make this 10 centimeters. Okay, so what is the magnetic field strength? Come on, markers. We're almost done. What is the magnetic field strength 10 centimeters from the wire? Okay, well, First, you're going to switch markers so that you can actually see what I'm writing. Next, my magnetic field strength would be mu naught, which is 4 pi times 10 to the negative 7. The current that's carrying through that wire, which is 5 amps. And I'm going to divide it over a circle that has a radius of 10 centimeters. So that will be 1 over 2 pi times rate times 10 times 10 to the negative 2. 10 to the negative 2 because it's centimeters. So if I go through and I start scratching stuff out here, a pi divides a pi. A 4 divides a 2 and leaves me with 2. 2 times 5 is 10. 10 divided by 10 is gone. I end up with 10 to the negative 7 divided by 10 to the negative 2, which gives me 1 times 10 to the negative 5. So I'm going to just check that. Let's see. 4 times pi times 10 to the negative 7. Stupid calculator. 4 times pi equals times 10 to the exponent negative 7 equals, there we go, times 5 is divided by 2 is divided by pi is divided by 10 to the exponent negative 2 is 1 times 1 times 10 to the negative 5. Okay, lovely. There we go. So I need a unit for this, and the unit on a magnetic field is a Tesla, capital T for Tesla. Okay, that does not feel like a lot of magnetic field from this conductor. Well, just for some comparison, the magnetic field close to a permanent magnet is approximately 2 Teslas. Now that's not a permanent magnet you toss on your fridge. That's permanent magnets that you use in industrial applications, like the anyway, crystal magnets, ceramic crystal magnets. The ones where you actually have to work to separate them from each other are around 2 Teslas. If you were to look at the electromagnets inside of the most powerful things, like particle accelerators or MRI machines, the biggest magnetic field they can generate, and so that's the biggest magnetic field ever generated by humans, is around 10 Teslas. And of course the Earth has a magnetic field which is on the order of 5 times 10 to the negative 5 Teslas. So that's about this. So if you are within 10 centimeters of a current of a wire carrying 5 amps worth of current, you are experiencing a magnetic field approximately 1/5 the size of the Earth's magnetic field. Okay, so this only applies if the wire, technically it only applies if the wire is infinitely long, and that's obviously not a thing. But if we're talking about electrons, or we're talking about protons, or things in circuits, right, like the little bits that are nearby to your conductors, a piece of wire this long might as well be infinitely long as far as an electron is concerned, because they're teeny tiny. So this is not a bad approximation for microscopic applications. Lovely. So the way that this works, right, with your straight line conductor, as soon as you create a straight current path, you end up with a circular magnetic field that has to obey the right-hand rule. And my spatial perception is challenged here because the video is going to flip and it's going to make my right hand look like my left hand. So I think if I do this, that will maybe look correct to you. But then it's the wrong way on the diagram. So anyway, right hand rule. Look it up. You'll get a better idea of how that works. The question then is, well, what happens if I take my straight conductor and instead of having the conductor be straight and the magnetic fields be in a circle, what if I take the wire and I wrap it as a coil? So I'm going to erase this and then we'll try drawing that. Okay, so I'm going to take my conductor and I'm going to wrap it in a coil like this. And I'm going to run 5 amps of current. In order to sort of show what's happening here, I'm going to have to cut this thing up the center. So what you'll see then is a bunch of currents coming at you. And a bunch of currents going into. Okay, now again, because of this whole video is going to flip, I'm not sure that the direction I draw this is going to be correct. It should be following the right hand rule. So when you run current this way out of the board, it should be creating a circular magnetic field like so. Right? They should all be doing that. Okay? And because they're going into the board this way, it should be also circular, but instead of going this way, it's going in the other direction. Okay, now I'm going to pull the same trick that I pulled when I did the electric field inside a parallel plate capacitor. I'm going to add more current density, some more wires here. So just like electric fields, your magnetic fields can't cross each other, right? They're supposed to be drawing the pathways that test charges would give. So what I end up with, if I add a sufficient number of coils here, is that the field ends up stacking on itself. Once I get these erased, I'll be able to tell you what that means. That this field, which used to be circles going that way, if these get close enough to each other, then the field can't penetrate between them, and it has to do this sort of thing. Come up and around and do that. And if I added more charges in there, these little ripples would end up smoothing themselves out, right? More charges mean smoother ripples. More charges would mean smoother ripples, until eventually, if I can get a mole's worth of electrons flowing into and out of the board, I end up with these loops. And remember that these ones are going that way. So I get something like that. Do you notice that this side and this side ended up parallel? Well, that's really handy. The other handy thing that's happening in here is if I pick a place like here, it's pretty close to this conductor or set of conductors, so it's going to get a pretty strong magnetic field. And it's not that close to that one, so it's going to have a weaker field from that one. But if I add them together, I would get exactly the same value as if I checked this place. Right? By moving closer to that one, I get the same intensity from this as I did from this one here. And if I were to add up these contributions, all the contributions from this side plus this side, gives me a nice uniform and parallel magnetic field inside of my coil. So I keep drawing sandwiches. Maybe I'm getting hungry. So I end up with a field that does this sort of thing. It's got the curves on the outside of the coil, but on the inside, there's this nice uniform straight field. So inside of here, I've created this nice straight magnetic field. Okay. So let me get rid of this messier diagram down here because that's just distracting. Okay, so if you were to do this and run 5 amps worth of current through this particular coil, the way you get the magnetic field there, if you recall, just like the conductor, I had this permeability of free space, and it depends on the amount of current I'm driving through it. But instead of dividing that current over a series of circles as I expand outwards from the wire, I'm dividing it over the number of loops that are in here. So if I increase the number of loops, then I'd have more current flowing, which would increase my field. If I took the same number of loops and stretched it out over more distance, I would have less. So I've got to put this in here. The longer the coil is, the less the field strength is. The number of the more loops I have, the more intense it is. And so what I end up with here, that's the number of loops per meter. That's like a density of loops, or like a coil density. How many loops are there per meter? So your magnetic field inside a solenoid, that's what this is called, solenoid, is these two numbers, right? The permeability of free space, the amount of current you're driving, and then it depends on the coil density of that tube. So for this particular one up here, if I had 20 loops per centimeter, doesn't matter how long the coil actually is, I just need to know the density of those loops. Then the magnetic field that's inside there, mu naught, was 4 pi times 10 to the negative 7. I'm running 5 amps of current through here, and I'm going to do 20 loops per centimeter. So that's 20 loops divided by 1 times 10 to the negative 2 meters. Okay, so if I were to put that together, 4 times pi equals times 1 times 10 to the negative 7 equals times 5 for my current equals times 20 for my coils per centimeter and divided by 1 times 10 to the negative 2 gives me 0.013 Teslas. Okay. Now that's not hard, right? A centimeter is about that wide. If you can fit 20 wires in that kind of density, you don't need particularly fine wire to do it. 5 amps, that's not unreasonable. And what we've ended up generating is a magnetic field of this strength. Now, just because I don't know what a Tesla's worth, I'm going to compare this to the Earth's magnetic field. So if you take the 0.013 Teslas inside this coil I have proposed, and you divide it by the 5 times 10 to the negative 5, which is the Earth's magnetic field, that divided by 5 times 10 to the negative 5 gives me 251 times the gravitational field of Earth. So I've been able to take, well, the Earth's field, I mean, it can spin compass needles. We use it for navigation, right? Like it's, you can actually use it to generate current if you have enough wire and enough patience and coordination. The Earth's magnetic field is reasonably powerful. I mean, it saves us, keeps us safe from cosmic radiation, etc. And inside this silly little coil, which is made of things that I could make by wrapping a wire around a pencil, I've been able to generate a field that's 250 times that strength just inside of this little coil. So if you were trying to make something that needed a very powerful magnet, like an MRI machine, then inside of that thing there will be coils of wire wrapped around and around and around each other in order to make a nice uniform field in the center. If you want to see something like this, that you can get your hands on, if you find an old speaker from like a car stereo or whatever, something that's sizable enough that you can see it, if you tear that thing apart, on the inside there will be a permanent magnet that sits at the bottom of the speaker, and then there will be a coil that sits just over top of it. And the way a speaker works is that your radio sends electric fields through this coil, which turns this coil into a magnet that vibrates up and down inside of the magnetic field created by the permanent magnet. And this vibration gets translated to the atmosphere, and then it shows up as sound in your ear, and your brain can hear it, which is really neat, that you're turning like magnetic fields into some sort of coherent information that your brain can understand. Anyway, the problem sets are just some simple calculations of magnetic field strength, so I will set you to them.